Hi there, welcome back. This is our first lesson in our nuclear chem unit. So everything now will be posted under Unit 13, which is nuclear chemistry. So the topic of today is what is nuclear decay? And joining us is Miss Vampus.
Hi everyone. Like Miss Scanlon said, we're going to be talking about the different modes of nuclear decay. All right. For homework tonight, there's nothing. Let's just keep up to date by looking at the calendar, making sure you know what is to be expected from this unit. Okay. Anything else, Miss Scanlon?
Just that this lesson is basically note-based. So it's best if you follow along with the note sheet posted on the website that says nuclear decay modes. So jumping into it, what is nuclear chemistry?
So let's take a look at the definition. We're on the first slide. Nuclear chemistry deals with changes in or transformations of the atomic nucleus. All right, and there are four types of decay: alpha particle, beta particle, positron particle, and gamma rays. And we're going to be talking about these types.
So, kind of bouncing off of what Ms. Vampus said and going into more detail, nuclear chem talks about how the nucleus is changing, okay? And we're going to talk about this for the entire unit and different aspects of it. But there are different types of decay, and that means to kind of break down. And so these four types of things are the different decay modes of these nucleuses. So this slide kind of puts together what we know so far about chemical reactions and how our nuclear reactions are different. When we're talking about chemical reactions, we're talking about atoms being rearranged to form different compounds. And when these elements bond, we're talking about how these electrons are shared, or how they're transferred to form these different compounds. Looking at number 3, some of these reactions, if you're forming these bonds, release small amounts of energy. And when we talked about rates of reaction, we can kind of speed up chemical reactions by, heating it, adding concentrations, temperature, all these different types of things. Now, nuclear reactions kind of break some of the rules that we've talked about so far.
Right. So let's take a look at the first thing. Elements are converted from one type to another. And we're going to get into what this means in detail later on. Number 2 says protons, neutrons, electrons, and other subatomic particles are involved in nuclear reactions. Large amounts of energy are absorbed or released, and rates are not affected by temperature, pressure, or catalysts.
One thing to point out, though, is bullet point number 3 about energy. We know, according to BARF, break, absorb, release, form, that when you're forming a bond, little bits of energy is released. So if you think about it, when you eat breakfast, different bonds are forming and breaking inside your stomach, and a little bit of energy you feel energized after you eat. But if you eat breakfast and these bonds are breaking and forming, you're not going to explode. But with nuclear reactions, it releases so much energy, enough to bomb an entire city, to power a city for an extended amount of time. So the amount of energy is drastically different.
Right. All right, let's move ahead and talk about radioisotopes. The nuclei of some unstable isotopes, called radioactive isotopes or radioisotopes, split up, forming atoms with a different number of protons and releasing radiation. So that process is called radioactive decay. So radioactivity is the release of energy and matter that results from changes in the nucleus of an atom.
So this is kind of what we had mentioned in the beginning of the video, these different decay modes. So these radioisotopes, they're kind of unstable. And so what happens is that they go through one of these decay processes to kind of have that nucleus change into something more stable. And that's what we're going to be looking into in more detail. So the first type of radiation or decay is called alpha radiation. And at this point, if you don't have your reference table out, take it out and look at table O, because that will play a big part in what we're talking about. And an alpha particle is basically a positively charged particle identical to a helium nucleus. So on table O, you'll see it written as this with an alpha symbol, or you'll see it as a helium atom. So those two things mean exactly the same thing. So what happens is that a nucleus that's unstable here's your unstable nucleus in a box, will break down into something else and also release this alpha particle. So the uranium decay, so right here is an unstable isotope of uranium, and it spontaneously breaks down, and you can tell it's spontaneous because there's nothing else helping it out. There's just that unstable uranium atom, and it breaks down into a different element, which is thorium, and releases that helium atom. So one thing you'll notice here is that the mass of the product of the reactant on top, on the left side is 238. If you add the mass on both things on the right side, it's also 238. Same thing with the bottom number. And as we work with these decay equations later on, that is super important. So this thing needs to be balanced.
Right, and that's called conservation of mass.
Mm-hmm.
All right, guys, moving along. We're on slide 6.
7.
Beta radiation.
Yes.
All right, so this beta minus decay occurs when a neutron is converted to a proton, and in this process, it emits an electron. So beta particles, they are high energy electrons whose source is an atomic nucleus. Take a look at the example that we have listed for you down there.
So here we have a neutron, and it's being decayed through beta radiation. And it kind of seems kind of counterintuitive at first, but here is the electron being released. And if you look at it, again, it's all about balancing. The top number on the left side of the reaction is 1. And if you add up the mass on the right side, it is still 1, so that's balanced. And then the bottom of the left is 0. And then if we look at the right side, we have 1 and negative 1. And so that cancels out to make a 0. So even if it doesn't kind of make sense conceptually, as long as you can understand that it is balanced, you can see how it is balanced. And again, we're going to be practicing with this. That is it. Next, well, before I move on, next slide is going into beta radiation in more detail. Again, you see this carbon 14 breaking down into a form of nitrogen and releasing that beta particle. Again, you'll see that this is balanced.
All right, so now we're going to talk about another form, positron radiation, beta plus decay, also called positron emission. This occurs when a proton is converted to a neutron, and in this process emits a positively charged electron, also known as a positron. A positron is a particle identical to an electron, except that it has a positive charge. This sounds super confusing, and we're going to break it down for you now.
So you might have seen the word positron just to confuse you in previous questions, but all a positron is essentially is a positive electron. So if you look at table O on your reference table, you can see it's written as one of these two different ways. So a positron has no mass, but it has a positive 1 charge. So that is what that looks like. And again, if you can't totally conceptualize what these particles are doing, as long as you can see that, going on to this slide, that this balances the reaction. We're going to talk about these balancings soon. That's all you need to know. Moving forward, the last type of radiation is gamma radiation. So a gamma ray is a high energy kind of photon that is released by these radioactive isotopes. These gamma radiations, they're not positive, they're not negative, they just kind of are these high energy kind of photons or light particles. So gamma rays are written as kind of that Y shape with a 0 and a 0. There's no mass, there's no charge to it, it just kind of exists. Here are 3 different examples of how gamma radiation looks in a reaction. And again, it will tell you if it goes through gamma radiation. That's also, if this sounds kind of familiar, this is how Bruce Banner became the Hulk. He was experimenting with gamma radiation and stuff went wrong. In actual reality, that's not going to work. He would have died from radiation exposure. But a cool thing to kind of mention.
Cool. So this next slide shows the penetrating power, and you see how gamma radiation, it goes through these different mediums: paper, aluminum, thick concrete. So it cannot penetrate through thick concrete or lead.
So, looking at this, gamma radiation has the highest penetrating power, meaning it can go through the most amount of things. If you think about it, this is why nuclear power plants like Chernobyl and other places, they're surrounded by these giant thick walls of concrete. An alpha particle, on the other hand, has the lowest penetrating power, and something as simple as a piece of paper will stop it. That's why one of the reasons gamma radiation is so kind of dangerous, because it can go right through your body. So this picture right here is a picture of your leg. This is your knee. This is your femur. Gamma radiation goes right through your leg without stopping, and as it does that, it can change some of the things in your muscle and your bone and cause you damage. Okay. Now, if we asked you to separate these particles, you might think it's impossible, but it's not. So one of the things to kind of talk about, and what helps, is these charges of these objects. So here we have a lead block, and we have this radioactive material, and it's releasing a beta particle, a gamma ray, and an alpha particle. Now it's passing through an electrical field, and the top part is positive, and the bottom part is negative. Now you can see that the beta particle is being pulled towards the positive side, and that's because beta particles are negative. So again, table O can tell you that, and so can the notes. And remember, opposites attract. And that's why alpha particles are being pulled down to the negative side, because they're positive. Just a quick backtrack a second. If you think, well, alpha particles, they sound familiar, that is what Rutherford used to kind of shoot through his gold foil, and that's how he figured out the structure of the atom. Getting back on track, the gamma ray, remember, it doesn't have a charge, so it's not going to be pulled towards the positive or the negative. It will pass right through that center. It will not get distracted by the charge. Okay. Vampus, anything to add?
I think we're good over here. We're good. No, this is a really nice way to show like the charges and how they are positive or negative, and which way they would go based on their attraction towards what charge. Does that make sense?
Yes.
Yes.
Okay.
And and so this is a good way to show like how they can be separated.
Okay, moving forward, and we've kind of talked about this leading up to it, is writing and balancing these nuclear reactions. So here are the steps of how to do it and an example. And so you can read them But let's just kind of work through it. I always feel that it's easier to just kind of show you how to do it, because sometimes the words can get kind of confusing. So we know that the sum of the top numbers on the left side need to equal the sum of the top numbers on the left side.
And just a little reminder that that number Ms. Scanlon is talking about is the atomic mass.
And then, good point, Ms. Vampish. Again, I'll just add that right here. So 27 aluminum. The top number, remember, is the atomic mass, and that's the number of protons and number of neutrons. And the reason it can change for different elements can have different masses is because you can change that number of neutrons. This bottom number is the atomic number and tells you the number of protons only. And remember, that's specific to an element. Okay. So going back to this example, if we add up all the bottom numbers on the left side, it needs to equal the sum of the bottom numbers on the right side. So if we focus on the top one first, we have 27 plus 1 needs to equal 24 plus something. So 27 plus 1 is 28, and that has to equal 24 plus something. And you should be like, well, duh, that empty blank box has to be 4.
4. Mm-hmm.
Same process on the bottom. So we have 13 plus 0 gives you 11 plus something else. And so we know 13 has to equal 11 plus something, and that something is 2. And so there you have your 4 and your 2. But the question is, well, what is X? And this is where table O comes into play. And so that X is your helium atom. It's also your alpha particle, which can be written both ways. So let's jump into a few more practice questions. So again, here's table O before we begin. And you'll see these different notations, how they're written in an equation and their symbol. So just have this out and ready. You need to flip between this and your periodic table to kind of figure out what is going on. Okay.
We're going to do question number 1.
Mm-hmm. So we're going to break up our reaction where that arrow is. And so we know that the left side, the top number, is equal to 210. So that means the right side also has to equal 210. We already have a mass of 4. So what goes in this box is 206. Because 206 plus 4 gives you 210.
Because remember, both sides have to be balanced. So now we're going to look at the bottom number, the atomic number, and we also have to balance both sides. So what number plus 2 would give us 84 on the right side? Ms. Scanlon?
I'm going to say that is 82.
Yeah, I think so. 82 plus 2 would yield 84. Okay, so now both sides, it is balanced.
Now, if you look on table O, nothing has those two numbers. So what you have to do is find the element that has 82 as the atomic number. And so, remember, the atomic number, that bottom number, tells you what element you are using. And that is lead, Pb. And so if we're looking at what kind of decay mode this went through, here is your alpha particle, and that's what kind of decay it was. So that's what goes on the line. Okay. Next question. Get a different color. We have 8 on the left side. We have 8 on the right side for the top number. So that means we can't add any more mass. That number has to be 0. And then, what plus 4 gives you 5? Vampus, what plus 4 gives you 5?
I would say 1.
So a positive 1. And then if you look at table O, that's that beta particle. Sorry, the positron. A positive electron.
Okay.
Number 3, again, it works the same way. So we have 14 right there. What plus 0 gives you 14? The answer is 14. And then, what plus negative, here's where it gets a little bit tricky. What plus negative 1 gives you 6? And that is 7. So if you think about it, 7 plus negative 1 is 6. And then in order to figure out what element this is, figure out what element is number 7. And that is nitrogen.
Right.
Okay? Moving forward.
I think the most confusing part of this is like, you're probably going to have to review adding and subtracting negatives. I feel like a lot of students mess up on that part.
And that's totally understandable. We have a few more practice questions today, and all of tomorrow is focused just on practicing these, writing these decay equations.
Mm-hmm.
So number 4, we know that the mass for our mystery particle has to be a 0 to keep it balanced. And then the bottom number of our mystery particle has to be positive 1, because positive 1 plus 7 gives you 8. And again, that is, the symbol is beta, and that is your positron decay. Now it's very, very, very important to realize that what I'm writing right now are 2 completely different things. Yes, they both use the beta symbol, but one uses positive, and that is your positron. One uses negative 1, and that is your beta particle. And then lastly, number 5, the top number missing in our mystery particle is 234. And again, we know that because something plus 4 has to give us 238. And then our bottom number is 90. In order to figure out what element that is, what is element number 90? And that is TH, which is thorium. And that's it. And this is another example of alpha decay.
Awesome.
Okay.
So in our next slide, we have like a little summary chart for you guys to just review. Okay, and then we're going to go ahead and practice some Regents questions. But before we do that, anything to add, Miss Scanlon?
Not really. The summary slide kind of ties up everything. Kind of brings table O into play and everything, and it goes over penetrating power and shielding. So what this means is like, how can you protect yourself from this particle?
Right.
So if you have low penetrating power, something like a piece of paper or clothing is enough to stop it. Whereas if you have very high penetrating power, you need something like lead or concrete to stop it. So this is a great summary chart of what we're doing. And so let's wrap this up with 5 more questions to help you out with kind of what we've done so far.
Okay, great. So let's go on to question number 1. A sample of which radioisotope emits particles having the greatest mass?
Okay, so for this one, you have to look at table N and O to help you. So table N, we're going to spend more time on this when we get to half-lives, but it tells you what type of decay these elements go through. So if you find choice A on table N, you'll see that it has a beta minus, and again, that has a mass of 0. That top number right here is your 0. If you look at iron 53 on table N, that's a beta positive particle. Again, it has a negative, doesn't have any mass, but it has a positive charge. But again, that mass is still 0. If we look at francium-220, that is an alpha particle, and the alpha particle has a mass of 4. And that pretty much looks like our answer, but just to cover up all of our bases, choice D, H3, is a beta minus. And again, that has no mass. So the best answer here is answer choice C. So again, you're using table N to figure out what type of decay it is, and then table O to figure out the mass of that particle.
Awesome.
Okay. Number 2 says, what is X? What element is represented by X? And so we have to find the top number and the bottom number. So Ms. Vampus, how would you go about finding that top number?
Well, I have to make sure that the masses are conserved. So the top number of that X plus 4 would have to equal 232.
I would... Okay. So...
Okay. So 232 minus 4 is 228.
Yes.
Okay. So that would be the top number. Now let's take a look at what the bottom number would be. It would have to equal 90. So X plus 2 would equal 90, which is 88.
I would totally agree with you. Now, that leads us down to answer choice B and D. Now, both of them have the right numbers we're looking for, but now what it comes down to is what element it is. And so I've been thinking, well, how am I supposed to figure that out? And again, you have to look at this bottom number. That bottom number is the atomic number, and it's the ID number for that element. So only one element has that 88 as the atomic number. And so if you flip to your periodic table, it is answer choice B. Element Ra is the only one with 88 as the atomic number.
That's right.
That is super, super important to go back and check. Okay. Number 3, it says positrons and beta particles have. So a positron, remember, is this symbol. 0 mass, a positive 1 charge. A beta particle is a 0 mass, a negative 1 charge. And so, using table O for that, that tells us that the answer is C. So the
different charges and the same mass.
The charges are different. One is positive 1, one is negative 1. But the mass, they are both 0. Okay.
Cool.
Number 4 says, which 2 radioisotopes have the same decay mode? So you need to use table N for this one. Without it, it is literally impossible unless you've memorized it. And at this point, you didn't even know it existed, so it's impossible.
Pretty much.
Okay, so when you find all these 8 elements, you'll see that calcium 37 is beta plus, iron 53 is beta plus. So that looks like our answer, but let's just keep going because this is fun.
Let's just double check.
B, francium 220 is an alpha particle, and cobalt 60 is a beta minus particle. So that's not the same, can't be B.
No.
If we look at C, potassium 37 is beta plus, and potassium 42 is beta minus. Yes, K is potassium, but no, this is not the right answer. And lastly, part D, TC99 is beta minus, and neon 19 is beta plus. That's not the same. Can't be D. So our first guess with choice A was correct, and we can even back it up.
Yeah, not so much a guess, but we supported it. Okay, very nice. All right, guys, so let's move ahead to our last question, number 5. Which nuclear emission has the greatest penetrating power? And we spoke about this, and you can use table N or O. You also have the notes to help you to answer this one as well. Okay. And what is our answer?
That would be gamma radiation.
That's right. So remember in our little chart, it said that it has very high penetrating power, and some of the materials that would stop it would be lead and concrete.
So again, that's just kind of a fact you just need to put into your head that gamma radiation has the highest penetrating power and goes through the most amount of things.
Right.
On that note, that is it for the intro video of nuclear chemistry. Tomorrow, we are going to focus more and practice more on how to write and balance these nuclear equations. So if you're still kind of confused, totally okay. That's tomorrow's plan. There is nothing due for homework tonight. Actually, I lied. The fighting power of soap case study, so the organic chem case study, if you haven't already submitted that to Google Classroom, that is due tonight, but nothing nuclear related. I had nothing else to add. Ms. Mampus, do you?
No, this was a pleasure. We miss you and hope everyone is doing well. Okay, make sure you submit your stuff and keep submitting stuff that you haven't. And we hope you have a great day or night.
Have a wonderful day. Bye.
Bye, guys.